Today we'll be talking about the starting point of amplification using BJT. So let's get down with it. So let's we can see some equation written in the center of the screen. These are actually for the common emitter circuit for the BJT. So what is the circuit we are considering? The circuit is something like this. We are considering a simple circuit something like this. So AC plus DC again at the input. Okay, so there is the resistance. This is definitely my supply voltage. Okay, you can easily understand from the notation, the capital letter and the small letter mixture, that it is DC plus AC. So this component is DC and this component belongs to AC. So DC plus AC component. This is the AC component right here. Okay, so IC is equals to, you can see that this is the equation written here right here. So how it had arrived, let me give you some hints about it. So if you talk about the AC plus DC, we'll be writing this equation very easily. We can write this equation: IS e to the power small v BE. So AC plus DC in VT, right? You can write this equation. So if you break down this VBE using this, you can easily write from there. You can easily write this equation, that is IS times e to the power VBE divided by VT, considering this the value of n is 1, multiplied by e to the power VBE by VT. Okay, now you see that this portion is nothing but a AC current, that is IC into e to the power VBE divided by VT, right? Okay, so we have found this, right? So a DC component right here multiplied by this AC component right here. Okay, fine. So from here, how we are jumping to this point, I'll be talking about that right now. So let's erase this thing for you guys. Let's erase this thing all. Let's erase this to the further calculation, manipulation of terms, so that you can easily understand. Okay, now let's begin. So okay, so here we are at this point right here. So what can we do? So see that our AC, this is my VBE, it will be a small, very small, very small signal AC, right? It's a very small AC. So for very small value, e to the power x can be written as 1 plus x and so on. Okay, so if I actually break down this, then I get something like this, that IC times 1 plus it becomes, so this is the value of x right here, right? So VBE divided by VT, right? Now this becomes something like this. Now you see that you can easily understand. Now you have IC time plus IC divided by VT by VE. I have neglected the higher order, the square terms, because the values are too small to be considered. So you can see that this equation now appears. It is formed in this manner. Okay, so here you can easily understand this portion is completely a DC component and this portion is my AC component that we are talking about. Now let's further erase some things to discuss something more. So the AC component will be actually manipulating that. So right now we have figured out how this equation has come. Now let's talk about the GM, or transconductance. So transconductance is something that it is the opposite transfer conductance. Okay, conductance means the opposite of resistance, and transfer means there will be a relationship between output and input. Now if I talk about that, so that from this equation, this is DC and this is the AC portion, right? So the AC portion is indicated by small letters. So small I, small c is equals to, now I can write IC divided by VT into VBE, right? Okay, now see that if you talk about this circuit right here, so VBE is your input, and for VBE you will be getting an output current of a small IC, that is AC current. So if I manipulate this equation into something like this, just think about it, something like this, that IC by VBE, so output by output current by input voltage. So current by voltage is equals to actually transconductance, that is your GM. You will be finding GM, and GM will be this equation. Now GM is equals to IC by VT. And what is R pi? R pi is the base resistance. We'll be needing this for our calculation. We'll be talking about it more. So the equation right now stands VT by IB. So let's talk about more of the amplification process. We know the characteristic curve of BJT, and we'll be taking the active region. This is active region for our amplification, because in active region we get a good amount of slope right here. Okay, and we're putting the we'll be actually drawing a curve. You know that by now, if you have seen the MOSFET videos, so then you take a Q point and you put the at that Q point, you take this Q point by shifting your DC biasing at the base, and after you're satisfied with a certain value, like right here in the middle, so then you put the small AC signal, that small VBE. That small VBE, then this is the small VBE, you can easily see here, right here, and then this gets amplified, because this is see the curve right here. It is your it is a curve. You can easily see this one right here. So there is this slope, higher slope. For this higher slope you get a amplified output, right? You get an amplified output. Okay, so this is the reason. Similar reason I discussed this thing in the MOSFET, so I'm not going to discuss it again. So that is the reason we choose active region. We bias it in the active region by putting a DC voltage at the base. Then we put the small AC signal, which is very low voltage, like millivolts, and then we get a good amount of gain. So now let's move on to the next thing, that is when we'll be analyzing the BJT. So when we'll be analyzing the BJT, okay, when we'll be analyzing the BJT, so we need to actually draw an equivalent circuit, for it to analyze it easily, properly. Okay, so there are two ways of drawing this thing. One is, you can see that this BJT, that is the collector, emitter, and this the base point, can be drawn as something like this or something like this. So you can easily see that there is a current dependent current source, which the value is GM into VBE. GM is your transconductance. You will be finding it by dividing IC by VT, right? And the VBE is the voltage across this R pi. You can see that the voltage across this R pi. So the value of R pi, you can find it by actually doing this, VT by IB. If you divide the thermal voltage, that is 26 millivolts, divided by IB, the DC base current, then you will be finding the R pi. Okay, so the voltage across R pi will be used in this value, GMVB. Okay, so this is one way. Another way is you make the dependent current source to be dependent on the current. Okay, so it's a current controlled current source. This one right here is a current control. You can see that current controlled current source, and right here is your voltage. This is the voltage. VB is a voltage, so it's a voltage control current source. I'll be using this one right here for my future calculations. So these are equivalent circuits for BJT. So this is known as hybrid pi model. Okay, now if you talk about practical consideration, so that is something like this. You get a slope at the active region. This slope actually means the R0, that means output resistance, is actually not infinite but a finite value, and it is somewhat big. Okay, it's a finite value. It's not infinite but a finite value. This actually reduces your gain. Okay, so if you consider a practical scenario, then you should use this sloppy output. That means your R0 is finite, and where to put it in the equivalent circuit? You need to put it in between the collector and emitter. You can see right here, this one right here, or this one right here, anyone you like. Okay, thank you guys. Hope you enjoyed the video. If you have any question, please ask. You can comment at the video also. Thank you.